I didn't know it could do that. I suppose you get locked out of your car. Like how I get to the camera now.
You were like, hey, mom, I'm up there.
All right, so where we left off is we had just done this example. We were doing a one sample t-test with some data, and we did a little reminder that when you have data, you gotta make sure if they don't tell you that there's an approximately normal distribution, or if they don't tell you that the population is normally distributed, you have to establish that, okay? So this example, I gave you a Minitab printout. On the AP exam, if you're given a Minitab printout, like let's say on a multiple choice, I want you to know where the necessary information is. But what I'm going to do is I'm going to treat this problem like we didn't have that, okay, other than the basic stuff. So it says a researcher plans to conduct a study to determine how 3 different types of treatments affect depression in adults. Assume a score of 4.0 on a particular test is considered typical depression. Lower scores indicate less depression and higher scores indicate greater depression. The depression of a simple random sample with 40 participants is measured, and a one sample t-test is used to determine whether the sample is representative of the population. So in other words, if we want to be representative of the population, we don't know whether it's higher or lower. We just want to find out, is this appropriate or is it not? Is it different? So this is Minitab output, but again, let's just go through this like we didn't have all of this information. So we're going to do a one sample t-test. And we have to start with conditions. And we have a known random sample. It was stated. Independence, you could say that each individual is independent of another. I get it, but we'll also quantify. We'll do our 10% condition. 10 times our n size, which was 40 participants. So 400 has to be less than our entire population. I think we can safely assume there are more than 400 adults in this population. And finally, our normal condition. I'll say it again. If they tell you, make sure you pay attention because sometimes they do. If they say the population is known to be normally distributed, great. You could say stated like we did with random.
If they say like the population distribution is symmetrical and unimodal, would you be able to say it's normal?
Mm-hmm. Okay. Yep, I've never seen that. On
one of the questions.
Did they?
Yeah.
Okay, so then I have seen it. I just didn't recall. All right, so the normal condition here. Remember, on May 5th, you're taking your AP exam. A stranger will be reading your test. Your job is to impress upon this person that you know what you're talking about. So if this were me, I would say, not stated that we have a distribution that's normal. And I would also then say, but the CLT applies because 40 is greater than 30. So we can assume that the distribution is approximately normal. All right, so those are my conditions. My null and alternative hypothesis. Null hypothesis has to use a population variable. So mu. 4.0 is considered typical. Alternatively, is it different from 4.0? Where mu is the true mean score on this test for depression. All right, now we do our T statistic. All right, so here's where we are going to look at the Minitab printout a little bit because you know enough about Minitab printouts. There's your n size, there's your mean, there's your standard deviation. So let's use those. So for this sample, the mean came in at 3.723. Call that an X bar. minus the mu was given as 4.0, divided by the standard deviation, which would be S or SX, 0.737, but then we have to divide by the square root of our n size. All right, what do I have this comes out as? I have negative 2.38. All right, so if I were to draw a sketch of that, I would put a t statistic of 0 dead center, and negative 2.38 puts me down here. So I can tell just by that drawing, I'm going to write on my paper, what is the probability that t would come in smaller than negative 2.38? And you could pull out your calculator and do your normal, or excuse me, your TCDF. And I had that comes out to be 0.0111. That's a TCDF. However, this was a two-tailed test. So all we were trying to find out is it different from 4.0? Our sample happened to come in on the low side, but it also might have come in. Then we have to mark over here, if this is a t statistic of negative 2.38, we're going to automatically mark the symmetrical equivalent, and you would now have the probability that t is greater than that. Or what you can also just do is, let's just double this. All right, so now that's what we call our p-value. Is our p-value less than our alpha? What is our alpha? Did they tell us? So which alpha do we assume they probably used? All right, not only do we assume that they used alpha equals 0.05, in the Minitab printout, do you see where it says 95% confidence interval? They used a 5%. That kind of gave it away right there. All right, so is P smaller than alpha? Yes. So we would, in fact, reject the null hypothesis. You may not end here. You make a concluding statement. We have convincing evidence that the true mean score of depression on this test is not 4.0. Now, I'm not going to say anything more than that right now, other than if you go back and read the stem of the problem, what they were doing was they were testing 3 different treatment types. So really what you could probably safely continue to say is, we have evidence to support that these new treatments must be changing the mu, okay? That we think these treatments are impacting the mean depression score. Now, would we want to safely say that it means that we're coming in lower? Now you might be stretching it here. Now you might be stretching it, okay? What I do want to point out, let's go back up here. Did you see the T?
Yeah.
In the past, when I've given you Minitab printouts, I've kind of circled things. I'm like, this is all you care about. This is all you care about. Don't worry about this. You are finally learning about what some of those things are. That really is your T statistic. So if you're on a multiple choice problem and that is up there, trust it. And look at P. And notice how it was already doubled, okay? Because this test said mu equals 4 versus not equal 4. It was doing a two-tailed test, which is the default for Minitab. This number, by the way, standard error. You know from your formula page that standard error is the standard deviation divided by the square root of the n size. Well, you know what? If you pulled out your calculator and you did the standard deviation divided by the square root of 40, yeah, that was it, 0.117. So that 0.117 was this right here. That was also up there in your Minitab printout. So you literally know what all those things mean now. Interpret the p-value in context. You should really know what this number represents. That's called your p-value. What that number is saying. Okay, first of all, let's back up. This was all based on this assumption. So you start by saying, assuming the true mean score on this test is 4.0. You've got to start with that. All the math was based on that. Assuming the true mean score on this test is 4.0, the probability, that's why it's called a p-value, of obtaining results equal to what we observed or more extreme is about 2%. And that ultimately is the reason that we reject the null hypothesis. This goes back to what I've been doing with you guys since October, when I'd say, what do you think? 2%. Could that maybe just happen? And back then you'd be like, well, that's kind of small. It's like, yeah, it is kind of small. This probably, if something only has a 2% chance of just happening, I wouldn't expect it to happen. So the fact that it did tells me something must be wrong. And all I can do is back up and say, you know what I think must be wrong? The original claim. Because I know I did all my math correctly. So if there's only a 2% chance of this happening, I think the 4.0 was wrong. So that's why we reject the null hypothesis. Now I also put down here, confirm the 95% confidence interval in the Minitab output. Let's just review this because we should know how to do this also. All right, so a confidence interval. It's almost like pretending like you didn't know what mu was. So you take a sample and it comes in at 3.723. Plus or minus, you need a T star. Now be careful, a lot of people are like, oh, 95%, that's the one she told us to memorize. That's 1.96. That is if you're doing a Z interval. Okay, for T, it depends. The n size impacts it. We'll come back to that. But then I can put in here my standard error, which was the 0.737 divided by the square root of 40, which remember, by the way, we actually already know is about 0.117 because it's in the Minitab output. All right, do you remember how to get the T star? Okay, can you picture a bell-shaped curve with 95% in the middle? Okay, because the T distribution is really very similar to a bell-shaped curve. Okay, so if you got 95% in the middle, the two tails together are worth 5. So how much is that tail worth? 2.5. Then that's what we do. We do an inverse T with an area of, I got my old calculator out here. Okay, area of 0.025, degrees of freedom 39, because the n size was 40. And it will come back, now this is going to say negative, but just ignore it. 2.023. So I could figure out my margin of error by taking 2.023 and multiplying by, remember, you know what this is. It's up in the Minitab output. It's 0.117. So my margin of error is about 24. 0.24. And then 3.723 plus or minus that. So 3.723 minus 0.24. 3.483, comma, and then I'm going to go back and highlight that, but just make the minus sign a plus sign, 3.963. Now, it's not exactly what we have up at the top, but it's all the round off error that we did. Okay, that was rounded, the 0.117 was rounded, and then I rounded that. There's a lot of rounding here. But my point to you, how does this interval confirm your results from part A? Okay, and that's why in some ways the confidence interval is almost more meaningful than the test. The test just says reject or fail to reject. This, you could come to a conclusion and say, okay, the 4.0 doesn't seem right to me. I not only would confirm rejecting the 4.0, but at least now I also have a plausible. So now I do think that the true mu is probably at a little bit less than 4.0 because I have my confidence interval to support that. Okay. All right, you ready for one last example? Did you remember to put the data in your calculator like I asked you? I should have reminded you guys while we were all just hanging out, but if you haven't put this in yet, please do. I did this example on my 84 last hour, so I already used that. So I'm going to actually do it in my Inspire because I have the data and I haven't touched it yet. Okay. So this example, I like to end chapter 9 with this example because it's actually also a great precursor into chapter 10. Because what chapter 10 is going to do, you're going to do all the same stuff, confidence intervals and statistical testing. But instead of having only one sample, you're going to have two. And you're going to learn how to compare. Let's just say one data set is, males versus females. Or maybe one group of students used one method to learn how to read. And another group of students used another method to learn how to read. And then you compare and you try to decide, did one method end up with better results than the other? But what happens is you also can do two sets of data that become what we call a matched pairs. Okay, we learned about that back in chapter 4. And that's what's happening here is every participant, there are 14 people here, and they are being given two different diets. Okay, these are all people trying to lower their cholesterol. So what they did was they randomly said, okay, you are going to randomly start by eating a diet rich in cornflakes. Okay, they decided to look at Corn Bran to see if that maybe helped. Okay, so let's say half the participants start by eating cornflakes every morning for breakfast, and the other half start by eating oatmeal every morning for breakfast because we're going to test the cornflakes versus oat bran. At some point, they're going to measure cholesterol and then switch diets. And then we're going to measure their cholesterol levels again. Okay, so that's what these are. These are the measurements of their cholesterol levels when they were eating cornflakes. This was cholesterol when they were eating oat bran. And you think back to chapter 4 and you can think about that they had to randomly decide who was going to start on which diet. They couldn't all start on the same diet because then maybe the results are simply because of the change that everyone did the same thing. Okay, so bottom line is when you do a matched pairs like this, what I tell my students to do is kind of look at the two columns of data. If these are their cholesterol levels, and we're looking, remember, to lower cholesterol, which of those columns in general looks like they have lower cholesterol? All right. So I like to start with that because, we talked about even in algebra, whenever we deal with negative numbers, we just make dumber mistakes. So whenever possible, I like to keep things positive. Because what we're going to do is we're going to subtract. You're going to make a third column in your calculator. Okay, if you're in an 84, I'm assuming this is in your L1 and your L2. You're going to make a third column of L3, which is going to be defined as L1 minus L2. If you're on Inspire, of course, you have to name your columns. Maybe you'll name this difference, and you're going to set it up as corn minus oat. Now, why am I doing it L1 minus L2? Because for the most part, the answers will be positive. Okay, as I recall, there are two participants that actually, it was reverse. Yeah. But in general, if you want to work with positive numbers, just glance at the data first. Okay, so I haven't done my subtraction yet, so I have to make my new column in my Inspire. All right, so I'm going to call it DIFF for difference, and then I'm going to define it as corn minus oats. All right, that now becomes your data set. You don't have two data sets anymore. You now have one. All you care about is that column and L3. Okay, that's it. So now we are off to setting up our test. All right, so we are going to do a one sample t-test again, and we're going to try to determine if the cornflakes really are better than the oat bran. We can see 12 out of the 14 people it was, but even that wasn't statistically significantly so. All right, do we have random something or other? We do. We have random assignment. Random assignment was described. Got it. I'm sure each participant is independent of another, but I'm also going to quantify by saying 10 times 14. I think I can safely assume the population was larger than 140 adults. And I'm assuming we're dealing with adults who have high cholesterol who are trying to lower it. But I think we can safely assume there's more than 140 adults who have high cholesterol. Do we have a normal distribution? It is not stated. So I'm going to say not indicated. And the CLT does not apply this time because my N size is only 14. I have only 14 participants. So now we have to look at pictures. We want to look at a box plot, perhaps, a normal probability plot. And remember, do not describe those two graphs as normal. They're not. On a box plot, you are looking for approximate symmetry, or a reverse way of saying that is you don't want severe skewness. You don't want to see outliers. And on the normal probability plot, you are looking for approximate linearity. All right, so here I am in my Inspire. You guys know how much I like my Inspire, but whatever. Okay, I got to go. Where am I? Where's my document? I don't know. Cholesterol, that's it. Okay, I need a new page. I'm going to add a page. I'm going to add option 5. There's all my dots. I'm going to come down here and tell it I want to use only the one called difference. And I don't want a dot plot. I want a box plot. Give me a box plot. Boom, got it. All right, now, I definitely see a little bit of skewness there. Okay, I got a left whisker that's much larger than my right whisker. But what I'm really glad I don't see, no outliers. So I'm going to address what I see. I'm going to kind of draw it, and I'm going to say, shows some skew, but no outliers. Again, think about it. You're trying to impress this person who's reading your test. You understand that you're looking for that symmetry. The skewness kind of caught your eye, but oh, no outliers. And then I'll quickly change that into a, to be honest, if I was running out of time on the AP test, I wouldn't even do this. I would just keep going. Okay, I prefer 2 graphs, but the fact that that one didn't freak me out, okay, if you had to, skip it, but we have time, so there it is. All right, that over there. That, if you remember when we first did normal probability plots, I said whenever there was a little bit of a vertical stretch, that was an indication of skew. Because what that indicated was all these dots were just data's collecting, but at the very end, the data collected quickly. Okay, that's all this data that's all scrunched in that tiny whisker. That vertical tail over there on the right side is actually kind of the equivalent of seeing the left skew. Okay, so again, if this were me, I would kind of sketch this and I would say, right side indicates a little skew, but generally linear. Distribution can be assumed approximately normal. And you might even want to say the distribution of the differences. Okay, maybe you even want to say this. This is box plot of the differences. This is the normal probability plot of the differences. Again, indicating something that you realize that I've created a third set of data, that's now the one that I'm studying. What it also means is when you start defining your null and alternative hypotheses. We're using a mu equals. You are dealing with the mu of that new column. You might even want to put a mu sub d so that it reminds you and them. This is the mean of the differences. Now, what we're trying to find out is one better than the other? Okay, we think, just by looking at it, we think, oh, brand works better. And the way we did the subtraction is, I did the subtraction L1 minus L2 because I did bigger minus smaller because I knew those answers would mostly come out to be positive. Right there, greater than 0. The null hypothesis is that the mu of the differences is 0. In other words, what this means, just so you know, it means there is no difference. The null hypothesis is we're going to assume that cornflakes and oat bran all do the same thing. Now, we looked at our data and we're going, oh, I think cornflakes wasn't as good, but you have to start with the null hypothesis. There's no difference. And now I'm going to find out, is there a difference? Is that one really better?
Why wouldn't you do that?
Because what we are trying to find out is, does it say in here? No, it does not say. You probably could. Okay. But very often what happens is we set this up based on, so yeah, you probably could. All right, so I'm going to say that mu sub d equals the true mean difference between cholesterol levels on the cornflake versus oat bran diets. So in your head now, you have to remember everything you do now is based on the column called differences. So when you set up your T statistic, when you have your X bar, it's got to be the X bar that came from your differences. Oh, I didn't do that yet. I didn't figure out what that was. Let me go back to that page. Let me quick do my one variable statistics off of the difference column. Okay, there's my X bar, 0.36, well, 0.36 or 363, whatever, minus mu sub d, 0, assuming there is no difference, over my standard deviation from my sample, 0.41, I think it looks like, divided by the square root of 14. And I had that comes out to be about 3.34. Now, even without doing the math on that, that's a pretty big T statistic, which means the p-value is going to be very, very small. Because if we were to draw a picture of that, we, of course, are way out here. So the probability that a T statistic comes in greater than 3.34, I have it comes out to be 0.003. So would my P be smaller than my alpha? What alpha are we using? Okay, by the way, since it doesn't tell you, go back and write it up here and make it part of your work, okay? So is our P smaller than our alpha? Yes, and it really wouldn't matter which level we used, okay? So we would reject the null hypothesis. We have evidence to support the claim that the cholesterol levels on the cornflake diet are higher than cholesterol levels on the oat bran diet. And again, evidence to support. And this is literally, when you see all the stuff like ads for the medications, or you see advertising for different diet plans that you can do, Nutrisystem, Jenny Craig, clinical tests have shown that, blah, blah. This is literally what they've done, okay? They literally have done tests to show that they can safely say without getting sued that we have evidence to support what we're saying. Okay, so we're going to when we recommend an oat bran diet, it's because, this is what our data show. Okay. And that is chapter 9.
So are we not going to use, because in this calculator, there's two simple.
We will eventually, as I said, that's chapter 10.
Oh, okay.
But what's going to get really hard in chapter 10 is there are some times that it's going to be a matched pairs like we did here. Other times it's not. And then you have to do the two sample. And that's what's going to be really hard. Now, what will make it easy is if the end sizes are different, then it can't be a matched pair. But when the end sizes are the same, we now have to stop and say, okay, are we matching or are we just having two groups? And that gets really challenging for some people, including me. I always hope when you give me two